In this video, we'll talk about sequential circuits and sequential logic. We'll also introduce latches and flip-flops, some basic storage elements. And then finally, we'll do a sequential analysis example. Okay, so far, we've focused on the design and analysis of combinational circuits, which were circuits where the outputs were functions entirely of the inputs and the inputs alone. So for any given input combination, I can determine exactly what the output will be. Sequential circuits also have combinational logic, but they also have some storage or memory elements. So for a sequential circuit, the output not only depends on the inputs, but also on the current state of the sequential circuit, where state of the sequential circuit is simply the binary information stored at any given time within the storage elements. And this is an important concept for sequential circuits, the state of the sequential circuit. Now, as you can tell then, sequential circuits can allow us to build more complex circuits, which not only depend on the current inputs, but also on what's occurred in the past, remembering some history with these storage elements. Or in other words, the output is dependent on the sequence of events that happen with the circuit. It may also be easier to implement a given application with a sequential circuit as opposed to a purely combinational circuit. Now, the storage elements in a sequential circuit are basically devices capable of storing binary information, and an important example of one of these devices is the flip-flop, which we'll talk more about in a second. This is the general form with which we can model most sequential circuits. Notice a big difference with a combinational circuit is that the sequential circuit has feedback. In other words, the outputs of my storage elements eventually, after going through the combinational circuit, feed back into those same storage elements. Another important class of sequential circuits, which today is by far the most common digital design approach that's used, are called synchronous sequential circuits, which basically means that these sequential circuits are clocked. And a clock is just a periodic signal that is used to synchronize the sequential circuit. Okay, so the first basic storage element we can look at is called an SR latch, and specifically an SR latch built with cross-coupled NOR gates. Now, most storage elements have some type of cross-coupled gates within their circuit. The cross-coupled NOR gate SR latch looks like this. And an easy way to remember the functionality of this SR latch is that S can stand for set and R for reset. So if I look at a condensed truth table for the SR latch, so S and R are my inputs, and the output Q, which I'll next produce, if S is a 1 and R is 0, then I'm going to set the state of my SR latch high. If I have 0, 1 on my input, so R is a 1, then I'm going to reset the state to 0. And if both S and R are 0, then the SR latch just maintains its current state. And in the case of the SR latch, a 1, 1 would be a forbidden state. So as an example, consider if both of my inputs were 1, and then S and R changed to 0, 0. When both S and R are 1, that will force both of these outputs of the two NOR gates to be 0. But then as soon as S and R change to 0, 0, depending on the timing of these gates relative to each other, my output will either be a 0 or 1. So for example, if gate 1 and its associated wires, their delay was larger than the gate 2 delays, then eventually my circuit will end up in the state where Q is equal to 0. But if gate 2 had a larger delay than gate 1, then eventually my circuit will end up in the state where Q is equal to 1. And so this is the reason why for the SR latch, an input of S and R of both 1 is forbidden and not used. Okay, now that we have the SR latch, which is a basic storage element we can create with just 2 gates, let's look at how we could add a clock signal to the latch. So we can go ahead and take our basic SR latch and add 2 AND gates on the front to AND with the clock signal. And so now this latch will only change its state or read the inputs S and R when the clock signal is high. So it sort of acts like a control input. But let's take a look at how we would use this component in a sequential circuit and some of the issues that might arise. So I have my clocked SR latch, has the clock signal connected into the clock of the SR latch. And then for my combinational circuit, let's say I have something like this. So I have the following combinational circuit, and I give a pulse to the clock signal. We'll assume my initial state is 0, and my X input is high. So at the beginning, my current state is 0, so Q naught will be a 1. X is also a 1, so 1 and 1 is 1, so my S and R values are 1, 0. And so my state, after propagating through the AND gate, is going to go high. And eventually, after the signals propagating through my clocked SR latch, from the inputs S and R to the output Q, my output will change to 1, 0, which is as I see here in the timing diagram. But at the same time, that's because I have this feedback loop, Q naught has now just changed to 0, so that 0 is going to come back around and change S and R back to 0, 1. And if my clock pulse is long enough, my inputs to my clocked SR latch again are going to see this change. And so then they're going to reset, because my S and R is 0, 1, and change the state back to 0 again after some delay for the signals to propagate through the clocked SR latch. So what I see then is that actually multiple times I could have these transitions before the clock pulse goes low again. This can make it difficult to design a sequential circuit where we only want one transition to happen in a given clock pulse. And so this is what leads us then to using synchronous sequential circuits and flip-flops. So a flip-flop is like a latch in that it's also a 1-bit storage element. But with a flip-flop, the inputs to the storage element are only read or triggered on an edge of the clock, as opposed to a latch, which we saw above, where the inputs were read whenever the clock was high. For a flip-flop, the inputs are essentially read on either the rising or the falling edge of the clock. So an easy way to think about this is latches are level-triggered devices, while flip-flops are edge-triggered. Both are 1-bit storage elements. So I could also have a flip-flop with an SR inputs, or more common, one of the most simple flip-flops is something called a D flip-flop. And if we assume that this is a positive edge-triggered flip-flop, then what we'd see is that, and the initial state perhaps is unknown, but on this first rising edge, on the first positive edge, the input X is high, so the flip-flop will have a value of 1 stored in it until I get to the next rising clock edge, where basically right before the clock edge I'm reading my input, which in this case is a 0, and then right after I'm seeing a change in my output of the flip-flop, and so I'll go back to 0 at this clock edge, and then at the next clock edge, again the input's back high, so again the state of my flip-flop will change high. Another thing to note here, flip-flops and synchronous logic elements usually use this symbol on the edge, this sideways triangle, to signify that it's a synchronous or edge-triggered device. And for negative edge-triggered devices, usually the symbol for the clock would also have a little circle in front of it to signify a negative triggered device. Okay, so there's different ways to build flip-flops, but let me just show you one way that we can build a flip-flop from our basic latch devices, our cross-coupled NOR circuits. So if I put 2 clocked SR latches in serial, and I'll connect my S and R inputs into the first clocked SR latch, and then I'll also connect the clock signal into this first clocked SR latch. So whenever the clock signal has a pulse or a high value, then the S and R inputs will be read and effectively change the state of my clocked SR latch. The second clocked SR latch, I'm going to invert the clock signal and connect it to the clock, and then go ahead and pass the outputs, the state of that first clocked SR latch, into the SR inputs for the second clocked SR latch, and this will produce my Q and Q naught values. So let's look at a timing diagram to see how this works. Okay, so on the first clock pulse, when the clock goes high, the first clocked SR latch, and I'm going to call this the master latch, is going to read the inputs the entire time that the clock signal is high. So S is 1, R is 0, so I'm setting the output of that first clocked SR latch Y high. Now, as soon as the clock goes low, this first clocked SR latch is no longer reading its inputs and is no longer going to change its state, and is going to be Y will essentially be constant at 1. But now, because my second clocked SR latch is the inverse of that clock, it now has a pulse, and it's now going to read the value y on its inputs, which in this case, y is a 1, so its output will also change to a 1. And because the clock signal for the first clocked SR latch is now low, it's not going to change, and I have a constant signal for the second one, and so I'm ensuring now that it's going to keep that value throughout that period. Now at the next clock pulse, again the first clocked SR latch is going to read its inputs, and in this case now S and R are 0, 1, so the signal will be reset. And then after the clock goes low again, then the second clocked SR latch, which I can also call the slave, will now read its inputs, which are constant, and so it will change its state to 0. So what I've essentially done is build a edge trigger device with these clocked SR latches. The inputs are essentially read the whole time the clock is high, and then the outputs only change on the falling edge are the 1 to 0 clock transition. And so this particular organization is called a master-slave SR flip-flop.